Welcome to this first MOOC, which is an introduction to plasma medicine. It will help students in biology and medicine to discover what are called plasma. It will also help students in plasma science and technology to better understand the potential of cold plasma as an innovative approach for biomedical applications. The outlines of these introductions are as follows. First, the medical context will be set. Second, we will discover how plasma medicine was born and how it is now applied. And third, the basics of cold plasma science and technology will be reminded. First, let's start with the medical context. Organ transplantation, cell therapy, surgical robots. Medicine surpasses itself to save and extend human lives or simply improve our quality of life. However, even up to now, medicine faces major limitations to cure legions of diseases and troubles. To illustrate these limitations, let us pause on two blatant examples. First example is head and neck cancer. It is the sixth most frequent cancer worldwide, which corresponds to squamous carcinomas from the upper aerodigestive tract. It represents almost 540,000 new cases per year. And even if there exist therapies combining ablative surgery, radiotherapy and chemotherapy, problems still persist. We have frequent relapse between 35 and 55% over 2 years, and a severe prognosis, since the survival rate is less than 20% on 10 years. So new therapies are highly expected. Another examples are foot ulcers in the diabetic patient. The destruction of the foot tissues can be caused by peripheral neuropathy. The consequences are an impairment of nerves, which induces loss of foot sensitivity and then a higher risk of accidental injury, and also a foot hydration that is reduced, inducing dryness, cracks, and calluses. So there exist some preventive solutions combining daily fit examinations, wearing appropriate shoes or cutting nails properly, but all those solutions only improve life quality, but they cannot be considered as curative treatments. Those two examples merely illustrate the fact that the conventional therapies, even if combined, remain limited, and therefore new therapies are highly expected, in particular innovative approaches at the interface of physics and chemistry. On that purpose, approaches such as PEF, pulsed electric fields, and therapeutic ultrasound techniques are studied for several years and even decades, but more recently another approach shows a promising potential, which is the science of plasma and more specifically called atmospheric plasmas. Here, the term plasma does not refer to the liquid component of blood which acts like an extracellular matrix to hold red and white blood cells. Here, plasma refers to a very specific state of matter, distinct from the well-known solid, liquid, and gas states. Before understanding the basics of plasma science and technology, let's introduce how medicine and plasma science have met to allow the emergence of a new research area called plasma medicine. The utilization of plasmas for therapeutic purposes is quite old. In 1893, during the World's Columbian Exposition at Chicago, Nikola Tesla presented the first prototypes of its violet ray medical appliance. Then, the invention aroused the curiosity of manufacturers and found its first domestical utilizations at the early 20th century. It was equipped with a variety of glass applicators, where plasma could be generated and applied on the body to treat nervous, dermatological, or muscular diseases and troubles. However, the success story stopped for two reasons. First, because of misuse by some people, and second, because of the Second World War conflict, which compelled manufacturers to reorient their activity to equip the US military forces. At the early of the 21st century, cold atmospheric plasma know a second birth to answer medical issues under the form of an academic discipline called plasma medicine. One can have an idea of its emerging nature by visiting the Google Scholar search engine and typing sentences like plasma medicine plus cancer or plasma medicine plus dermatology. Then, the annual number of articles published per year on these research activities can be measured. On this graph, we clearly observe that plasma medicine has started around 2006 and that the research works in cancerology and in dermatology have continued to grow inexorably. For this reason, the academic research in plasma medicine can be considered as emergent or exploratory. Plasma medicine is also highly multidisciplinary. Today, it is at the interface of plasma science, life sciences such as biology, clinical physics, and clinical medicine. And the convergence of these competencies is mandatory to build a unified knowledge. So now it is time to focus on one of the four disciplines taking part to this unified knowledge, plasma science and technology. The three basic states of matter commonly described in introductory chemistry texts are solid, liquid, and gas. However, such a representation is incomplete since a fourth state of matter exists under the name of plasma. Plasma can be classified into two main families, natural plasmas and artificial plasmas. In the natural plasmas, the first example that can be mentioned is the universe. More than 99.9% of the visible matter in the universe is in the plasma state. The solar wind is a plasma which passes through the magnetosphere tail. It interacts with ionosphere gases, giving rise to the aurora borealis. Other examples are lightnings. They result from electrically conducting plasma channels, giving rise to a brief but strong electrostatic discharge. Among the artificial plasmas, neon lamps figure among the most basic examples. The gas is contained in a tube and ionized by applying an electric field. Also, plasma display panels use small cells containing electrically charged ionized gases. And plasma processes are developed for surface treatments, using, for example, a matrix of corona discharges. To understand very simply what is a plasma, let's consider a system solely composed of water molecules. If the temperature is very low, then water is under the solid state. It corresponds to the ice cubes that you put in your soda. If you increase the thermal energy of these ice cubes, then they transit from solid to liquid state. This is the water you daily drink. If you increase again the thermal energy of this liquid, then it can transit to its gaseous states. It is the water vapor emitted, for example, by an iron. Finally, if electrical energy is injected into this gas, for example by applying an electric field, then a plasma can be generated. To be used in medicine, plasmas must meet specifications based on practical and medical considerations. If the plasma has to interplay directly with biological tissues, then it has to be weakly ionized. This means that for roughly 1 billion of natural species, less than 100 are electrons and ions. The plasma has to operate also at atmospheric pressure, and the gas temperature of the plasma must be close to the temperature of the human body. Since the plasma is in a thermodynamic disequilibrium, electron temperature is much higher than the ion temperature, which in turn is also much more higher than the temperature of the neutrals. Now let's talk about the plasma sources for the treatment of living systems. Plasma jets, surface DBD, and volume DBD have already been employed for the treatment of large areas, or on the contrary, of very localized regions, and even for the treatment of complex structures and geometries. Usually, a cold atmospheric plasma is generated by mediating a gas between two electrodes. One of the electrodes is connected to the electrical generator while the other is grounded. The resulting voltage applied along the interelectrode distance allows the generation of an electric field which, if it is strong enough, can ionize the gas, thus giving rise to a plasma. This plasma contains atoms and molecules excited to different energetic levels, positive ions and electrons, and eventually negative ions, chemical radicals, and metastable species. Most of the plasma sources rely on the same configuration, two electrodes separated by a dielectric barrier. Such discharges are called dielectric barrier discharges. Two main types of DBD can be distinguished, the non-flowing DBD and the flowing DBD, also called plasma jet. So let's first consider the non-flowing DBD. The structure of the non-flowing DBD is as follows: an excitation electrode, a dielectric barrier, a gap region where a gas can be ionized, and a counter electrode. The excitation electrode is polarized to an AC or pulse voltage, while the counter electrode is grounded. Hence, an alternative electric field applied in the gap region can generate a cold plasma. The dielectric barrier is of major importance, since it prevents any thermal arc formations. The electron avalanches are amplified, giving rise to plasma microdischarges developing at a nanosecond time scale. The main limitation of this device is the inter-electrode distance that has to be less than 1 centimeter. And as you can observe in this picture, the human skin here plays the role of the counter electrode, whose potential is not grounded but floating. The configuration of the plasma jet now is very close from the structure of the non-flowing DBD. In the kinetics, the voltage is delivered by an inner needle electrode, while the outer ring electrode is grounded. The electric barrier separates these two electrodes. Inside this tube, a gas is delivered upstream of the inter-electrode region. Usually this gas is helium or argon, but it can be mixed with other reactive gases such as oxygen. The input gas allows to extend plasma beyond the inter-electrode region, and therefore a plasma plume can easily be developed on several centimeters. Several advantages are noteworthy. First, hollow cavities are accessible, as well as very localized areas. The treatment of 3D biosystems, and also the lowering of the heating of the biosystem. The plasma can be applied on tissue located several centimeters away from the plasma jet and without inducing thermal damages, as can be observed here on this picture where a finger is directly exposed to this plasma plume. These plasma sources can be used following direct and indirect contact approaches. In the direct contact approaches, the biological tissues or tumor is directly exposed to the plasma. One can distinguish the case where the biological system constitutes the counter electrode and the other case where the counter electrode is integrated to the DBD device. Here, several properties of the plasma can present a therapeutic p-value: the electric field, chemical species, radicals and ions, the gas temperature, radiation, the gas flowing. And depending on their range in amplitude and intensity, some of these properties could present competitive or synergetic effects. The indirect contact approach can be performed via liquid or dry intermediate media. First, a liquid can be plasma activated during several minutes and subsequently injected in the tumor. Second, a therapeutic material or substance can be treated by plasma or subsequently set on the tumor. In this indirect approach, only long-life radical species can have a therapeutic p-value. The potential therapeutic effects of electric field or short lifetime radicals, such as OH, are absent. So, as a conclusion, we have to keep in mind that cold atmospheric plasmas are investigated as an innovative approach for the treatment of diseases where conventional therapies fail. Cold atmospheric plasma are weakly ionized gases characterized by several properties: electric field, chemical reactive species, energetic species, controlled heating, flowing, and radiation. Also, most of the time, they are generated using DBD devices, in particular plasma jets. They can be used following two approaches: the direct contact, where short lifetime species, as well as transient physical phenomena can have a direct therapeutic impact on the system to be treated, and indirect contact, where PAM, plasma activated medium, is synthesized and then interplays with the system to treat.